Hi, I'm Ramin Mojab. In this lecture, I'm going to talk about probability density and probability mass functions. Let me summarize the main points first. I'm going to talk about 4 different types of CDFs. I will define continuous random variable and a related concept, which is the probability density function. I will also define discrete random variable and again a related concept, which is the probability mass function. I will also talk about some examples. For example, the Poisson distribution, the normal distribution, a random variable with zero variance, and we'll interpret the indicator function as a random variable. Why do we need a classification of the random variables? I can think of 2 reasons. It can help us to explain the logic behind the definitions of the expected value and variance. I talked about it in the previous session too. It can also help us define probability mass and probability density functions. I will talk about these are useful concepts and I will talk about them later in this lecture. Anyway, X is a function from the sample space to a set which is a subset of a real numbers set. We know that there are 3 types of sample spaces. A sample space might be discrete, infinite discrete, or continuous. The question is, should we define 3 types of random variables based on this classification? The answer is no. We have a better choice, and it's better to focus on the characteristics of A, which is the codomain of this function. For example, omega can be a continuous set while A is a discrete set. For example, consider the floor function. The codomain of this function is, for example, n, the natural set of natural numbers. Anyway, we will focus on A, and A can be continuous, discrete, and a combination of these sets. In the next slides, I'm going to focus on the codomain of the CDF function instead of A, here the codomain of X. These are related to each other, and you can see this relationship in this formula. However, in order to explain this relationship, I provide an example. Assume that an athlete is practicing shooting at an archery target, and assume that this is the target, this is the center of the target, and this is an arrow, and we name this D, and we define a random variable X such that it is D if D is less than 5, and it is the floor of D if D is equal or greater than 5. This is just a scoring schema, and we want to be more exact when the distance is small enough. Here at this part, for example, if it's 6.6, then we transform it to be 6. The score is 6 here. Anyway, let's draw the CDF function, the capital F here. Assume that this is 0, and we know that the CDF is 0 at minus infinity. If this is 0, then the slope is positive here, and then we have a 0 slope again. There's a jump here, for example, and again the slope is 0. There's a jump here, and we assume that here this is 1, and we know that the CDF is 1 at positive infinity. By the definition of the random variable, this is 5, this is 6, and this is 7. This is the CDF of an athlete, and it can be something else. And here we are almost sure that the score of this athlete is 7 or less than 7. Now, here, if we focus on the vertical axis, there is a continuous set here with some values here, and there is a value here and 1 here. Here we have a set of 2 members, or discrete set. Here we have a continuous set. and here is a discrete set. Therefore, the codomain of this, the cumulative function here, is a combination of a discrete and a continuous set. Let's talk about different types of CDFs. In fact, we have a spectrum of CDFs. At one end of this spectrum, we have discrete CDFs. The values of a discrete CDF are distinct or separate, or the codomain of a discrete CDF is a discrete set. At the other end of this spectrum, we have absolutely continuous CDFs. An absolutely continuous CDF has derivative almost everywhere. This is the first condition. And there's a relationship between the value of the function and the integral of the derivative. You must be familiar with this equality. I'm not going to explain this. And this is the second condition. We have something known as differentiable but not absolutely continuous CDF here. And for such a CDF, the first condition holds, the second condition does not hold. For example, the Cantor function has derivative almost everywhere, and the derivative is 0 almost everywhere. In other words, this is the derivative of this function, and as you can see, the integral of this derivative is 0. Therefore, this part is omitted from this equality. But this is not a constant function. This, it does monotonically grow, and therefore this equality does not hold for these types of functions. And note that we are not generally going to talk about these types of random variables or CDFs in this session or our next sessions. If the CDF of a random variable is an absolutely continuous function, then we call this random variable a continuous random variable. And for a continuous random variable, we define the probability density function, or PDF, which is the derivative of the CDF. Note that since CDF is an absolutely continuous function, it has derivative almost everywhere. This is the first condition that we talked about in the previous slide. And if we use the second condition of the previous slide, then we can say that the value of the CDF is the integral of the PDF. Or another interpretation is that the PDF is the slope of the CDF. If you want to interpret the value of the PDF, you can note that the probability that x is between b and b plus a very small number is approximately the value of the PDF. For example, if this is the probability of this is the PDF of a normal distribution, of course I'm going to talk about it as an example later, then, and assume that this is plus 1, then this value is the probability that x is between 1 and 1 plus a very small number. And also note that the probability that x is a real number is almost surely 0, or it is an impossible, it is not an impossible event, but it is a 0 probability event. We talked about it in the second lecture before. We can prove two equalities here. Let f under x of x to be the PDF of x. Then we can say that the integral of PDF is 1. For example, if this is the PDF of the normal distribution, then the area of this region is 1. And it's easy to prove this one because this part, the left-hand side of this equation, is actually the CDF at positive infinity, which is 1. Here we have another important equality. If x is p integrable, which means e of x exists, then E of x is the integral of x multiplied by the PDF here. In order to prove this one, it's easy again, because we know that E of x is the integral of x d of f of x, capital F here. And we know that the derivative of this function is the PDF. We can use this equality and again talk about the logic behind the definition of the expected value. Here it says that we have here x, PDF of x. As the value of x increases, the importance of this probability or its probability increases too. We talked about this in the previous lecture. However, we can interpret or we can say something different. As the probability of x increases, the importance of the value of x increases too. Recall that this is the probability that x is greater than x and smaller than x plus a small value. Okay, let's talk about the other end of the spectrum, in which the CDF is a discrete function. If the CDF of a random variable is a discrete function, then it is called a discrete random variable. And for any random variable, not just a discrete random variable, we define probability mass function, or PMF, as the probability that x equals a real number. Note that when we define the CDF, we were interested in this set, x such that x is equal or less than a real number. Here we are interested in a similar set, x such that x is a real number. And the interpretation is easy. This is the probability that x equals b. Note that although we are introducing these two concepts in one slide, discrete random variable and probability mass function, we define the probability mass function for any random variable, including the continuous random variables. Therefore, of course, there is a reason behind this. This is because the probability mass function is actually useful for discrete cases, not continuous cases. We can prove some theorems here. Let x be a random variable. If x is an absolutely continuous random variable, then the PMF at b for all b is 0. Note that the PMF of value, for example, b, is the CDF at b minus this limit of the CDF at x as x approaches b from the left. You can easily check this one, because this is because PDF is the probability, capital P here, the probability that x is less than, for example, b, and this limit is the probability that x is here we have equality, here we do not have equality. And if we use this equality, we can say that, for example, assume that this is a CDF of a discrete random variable, then this distance is the PMF. Okay, and for a continuous case, this limit equals this value, and therefore the PMF is 0. There is another theorem here. If x is a discrete random variable, then the summation equals 1 is similar to the proposition we had before for the continuous case, in which this integral is 1. Here, in order to prove this one, again we should use this formula that the PDF equals the CDF at b, let it be b, minus this limit, the CDF x as x approaches b from the left. We should substitute this formula and note that A here is a set, is a discrete set. Assume that it's A1, A2, and AN, and also assume that A1 is less than A2, less than AN. AN is the biggest number, A1 is the smallest number. Here it's easy to see that the CDF at AN is 1. We know it from the properties of the CDF, and this limit as x approaches A1 from the left, fx x, this is 0. All other terms of this summation will be omitted, and therefore except this one, and therefore the value of this summation is 1. Here there is another theorem, you're familiar with this one, I think. If x is a discrete random variable and the expected value exists, then the expected value is the sum of these terms, the value of x multiplied by the value of the PDF. It's again similar to the previous formula. X for the continuous case is the x f of x d of x is this integral. Here, in order to prove this one, you should use the definition of the Riemann still just integral. Here Ex is actually this limit as n approaches infinity, sum of 0 to n, for example, sum of x ai. Here we are using this one too, again multiplied by f of x ai minus limit of x approaches ai from the left, fx of ai plus 1. So here we have plus 1, here we have ai. And as you can see, you can easily see this on a graph. If this is the CDF, then this difference is this one. For example, here this difference is 0 because the value of this 0 because for a small partitioning, these are these are adequately close to each other, and therefore their difference is 0, except this point. The difference is the PDF. The same is true here. The difference is the PDF, which is this PDF here. And AI is multiplied by some PDFs. Again, similar to the continuous case, this formula can help us explain the logic behind the expected value. Here it says that x is multiplied by the probability of x. It is more clear here. As the probability of x increases, the importance of x increases too, or as the value of x increases, the importance of its probability increases too. I will review our discussion by some examples. The first example is about the Poisson distribution. Assume that x has a Poisson distribution. This distribution has a parameter lambda, which is a positive real number, and this is the CDF of this random variable. As you can see, this is a function of x and lambda, and here this is the only place that x appears in this function, and this is the floor function, which means that the codomain of CDF is a discrete set, and therefore by this assumption we are dealing with a discrete random variable. And since it's a discrete random variable, we cannot define PDF, probability density function. However, we can define PMF, probability mass function. and its PMF, which is derived from this CDF, is this function. This is 0 if x is in this set natural numbers, the union of natural numbers as 0, then it has a value. Otherwise, it is 0. And we can also use the previous propositions and calculate the expected value and variance of this random variable, which is equal to the parameter of the distribution, lambda. And when should we use this random variable, or when should we assume that a random variable has Poisson distribution? Assume that on average an event occurs lambda times within an interval, then this PMF is the probability that such an event occurs less than or equal to x times within the same interval. The second example is about the normal distribution. Assume that x has a normal distribution. This distribution has two parameters, mu and sigma squared. Both are real numbers. Of course, note that this is a positive number, 0 to positive infinity. And this is the CDF of this random variable. As you can see, it's a function of x, mu, and sigma squared. And of course, I'm not going to explain the formula. What is important is that the codomain of this CDF is R, and it is a continuous, absolutely continuous function, which means that by this assumption, we are dealing with a continuous random variables, and therefore PMF is not useful. It's 0 almost everywhere. And what is more useful is PDF, and we can calculate it. This is the PDF probability density function. You must be familiar with this one. And again, it's the function of x, mu, and sigma squared. We can use this formula and prove that the expected value of x is mu and the variance of x is sigma squared. When should we use this assumption, or when should we assume that a random variable is normally distributed? If x occurs with expected value mu and variance sigma squared, then we can use this assumption. In this example, I'm going to talk about a special type of random variable in which it has a zero variance. Let x be a p squared integrable random variable, which means that e of x and e of x2 are defined, and assume that its values are in this probability space, and assume that omega has just one elementary outcome. This means that x is a constant. X is constant. There's just one w here. Assume that this is equal to c, which is a real number. The CDF of this random variable is a step function. This is the capital X. The capital F is actually 0 if x is less than c, and it's 1 if x is equal or greater than c. And you can show this step function on a graph too. For example, here this is 0, and this is, assume that this is c, then we have a jump here, and this is 1. This random variable, as you can see, this is a discrete set, and therefore this random variable is a discrete random variable, and it is known as constant random variable. And we can calculate the PMF of this random variable. It is equal to 1 if x is c and 0 otherwise, which means that this random variable is equal to c with probability 1. As we said here, it's a constant. The value of this random variable is constant. We can use the definition and prove that this is the expected value is c, and also the variance of this random variable is 0 because x2 is constant, and it's equal to x squared is constant, that is equal to c squared, and e is squared x is also equal to c squared. In the previous discussion, the sample space has just one elementary outcome, and we said that because of this, the variance of a random variable defined on this space is 0. This is a sufficient condition to get a random variable with 0 variance. In fact, a random variable can be almost surely constant, which means that there might be other possible values but with 0 probability. For example, consider this experiment in which a dice is tossed, and if it lands on an edge, you win $10, otherwise you win $2. This is a 0 probability event, and therefore the value of the random variable is 2. Of course, assume that x is the return in this experiment. And such a random variable is known as almost surely constant random variable. And we can use a similar discussion and show that the variance of this random variable is also 0. This is the last example in which I am going to interpret the indicator function as a random variable. We talked about this function before, and if w is in E, then the value of the function is 1, otherwise the value is 0. Now assume that E here is an event, it's a member of a sigma algebra, and W is a elementary outcome, it's a member of omega, and this is the probability space that we are talking about. And now assume that this is a random variable with values in this probability space, and we can talk about the cumulative distribution function and show that it's a discrete random variable. Here you can see that the codomain of this function is a discrete set, and therefore we can talk about the probability mass function of this random variable. If x is 1, then the probability is the probability of this event E. If x is 0, then the probability is the probability of 1 minus PE, or the probability of the complement of E. And otherwise, this is the probability is 0. It takes the values of x is just 1 and 0 here. Okay, the expected value of E, it's easy to show that the expected value is equal to the probability of E. This is because this is x with probability PE, therefore 1 multiplied by PE plus 0 with this probability, 0 multiplied by 1. So here we have E. E, which is P of E. We can also talk about the variance of this random variable. Note that the PMF of this random variable indicator function squared is the same as the PMF of the indicator function. And if we use this equality, we can show that the variance of this random variable is PE multiplied by 1 minus PE. Regarding the expected value of the indicator function, we proved this by using the probability mass function. And note that we can use the properties of the Lebesgue integral and prove this equality. This is what I'm talking about. This part is the expected value, and this equality is a definition that I talked about in the previous lecture. I leave it as an exercise. In fact, I want you to show that these 4 equalities are valid. For the first one, do not interpret the indicator function as a random variable, because we have not yet discussed the equality of random variables. Just use the definition of the function. This is the expected value that I talked about. use the first one to prove this one, and use one of the properties of the Lebesgue integral and prove the last one, this one. Thanks for your time. In the next lecture, I will talk about multivariate random variable.